Hi everyone. Now let's continue with the network laws and theorems. This time we have the Norton's theorem. What is Norton's theorem? It states that a linear two-terminal circuit which has several voltage or current sources and resistances can be replaced by an equivalent simple parallel circuit containing one current source, which we call it as IN, and one resistance, we call it RN. The concept of Norton's theorem is similar to the Thevenin's theorem that we discussed last time, that a complex circuit was replaced by a simple series circuit for Thevenin's theorem. But this time, for the Norton's theorem, we are going to replace the complex circuit by an equivalent simple parallel circuit. Let's consider this illustration. Okay, so as what I have told you last time, that the RL is variable. So if the value of RL is changed, so we need to make another circuit analysis to solve for the IL. To avoid that, in Norton's theorem, we are going to replace the complex circuit excluding the RL by a simple parallel circuit. So this is now the Norton equivalent circuit in which we have added back the resistance RL and we have this RN in parallel with the new source, current source IN. What is IN? IN is the current at the short-circuited terminals. RN is the equivalent resistance at the open-circuited terminals, or it is called the looking back resistance. You notice that we have the same definition of the RN in the Thevenin's theorem. So therefore, RN and the RTH are just equal. So we have the same method in solving for the equivalent resistance, or that is RN or equal to RTH. RL is the same, the load resistance, and IL is the current through the load. So our main concern here is how to determine the current IN and the resistance RN. As what I have told you, that RN is just equal to RTH. RN is just equal to RTH in the Thevenin's theorem. So in solving for RN, we have the same method. We have to remove the load RL and leave the terminals open. Set all the independent sources to 0. And then after that, we have to solve for the equivalent resistance at the open circuited terminals. Okay, next, we have to solve or determine the current IN. So how to find IN? Simply, we have to remove the load resistance RL only and replace by a short circuit. And take note that all independent sources are still in the circuit. Then we need to solve for the current at the short-circuited terminals using any theorems discussed, since the circuit consists of more than one source and it could be either voltage or current sources. So let's have this illustration and let's consider this figure. So our goal here is to determine RN. So solve RN. Okay, recall that in solving for the RN, we have the same method as with the RTH. We simply have to remove the RL and leave the terminals open, and then set all the voltages and current sources to 0. Now, let's draw the equivalent circuit. So we have to remove the RL and leave the terminals open. And then we have to set all the independent sources to 0. So since the sources are voltages, then we have to replace the voltages by a short circuit. And we have here the R1. Okay. So we have to disconnect the load RL and leave the terminals open. Okay, then we have R2. And then E2 is to be replaced by a short circuit to set E2 to 0. And then at the open circuited terminals where we can solve the Rn. Okay, and we will redraw the circuit. It can be redraw like this. Okay, so that it will be clearer that the R1 and R2 are just connected in parallel. So Rn then is the parallel combination of R1 and R2. So we have 1 over R1 plus 1 over R2. Okay, so the next step is we have to solve for the IN. So solve IN. So let's recall how to solve for IN. We have to remove the load only and replace by a short circuit. And take note that all independent sources are all together in a circuit. So we have here the E1 and the load will be replaced by a short circuit. Then we have the R2 and the E2. So we label this. Okay. So the current that flows through the short circuit terminals is, we call it as IN. IN, sometimes called as ISC, or this is the short circuit current. Okay. Now, how are we going to solve for IN? Since there are two source voltages, independent voltages, so we cannot use the series parallel strategy. Instead, we will be using, or we are going to integrate any of the network laws and theorems. Since current is the unknown through the short-circuited terminals, then we may choose in using mesh analysis. So let's call this as loop 1, current I1, and then we have here loop current I2. Again, the loop currents, their directions are arbitrary. So let's start. Let's have to write the voltage equation. We will be using KVL at loop 1 to write the voltage equation. So we have E1 minus, okay, it is, so when the current I1 flows through R1, so you have plus and minus. So since we are getting the sign, the outer sign, so you have plus and then you have here minus I1 R1. Since there is no element here, it is just a short circuit, so that's equal to 0. Automatically, we can solve for I1. That's E1 over R1. And at loop 2, we will be using KVL at loop 2. So we are going to follow the direction of the current I2, which is counterclockwise. So we will be getting the plus sign of the source. And then when the current flows through R2, you have plus and minus. So we have here E2, positive, minus I2, R2. Again, there is no element in the short-circuited. It's 0 resistance. So that's equivalent to 0. So I2 then is equal to E2 over R2. Now, what is IN? So if we have here at node A, so We'll apply KCL at node A. So current entering is equal to current leaving. Recall that KCL is just equal to current entering. The current entering is equal to the current leaving. So the current entering at node A, we have I1, and you have here I2. So you have I1 plus I2 equals IN. So if we have found the values of I1 and I2, so we just simply add them and we got the IN.